Well, hello, everyone. Thank you so much for coming to this presentation. I'm excited to spend the next little while with you. And there will be a period of time where we're going to have some a part in the chat. So if you want to utilize that feature, you're welcome to. And of course, we can do the Q&As at the end as well. So let me share my screen and we'll get started. All right. So hopefully everyone can see that all right. First of all, again, my name is KimberLeigh Hadfield and I'm from Utah State University. I teach large lecture sections of introductory statistics courses, and it's a lot of fun, but of course I can't just not have us have try and have an interactive day today. So let's get this rolling here. This is the citation. If you just want to use Google Scholar, type in my last name and then something like providing ability to probability, you can get the full article here where it does have links in the teaching statistics article to everything that I used in this experiment, this quasi experiment here, where I hopefully reduce some cognitive load through using some worked out examples. So anyway, that's all available online. So you can access all the full worksheets and everything that I did in this example here. So today I'm going to introduce the introductory statistics classes that I teach to you, talk about cognitive walls, and the research on cognitive load in education. I preface this right now with, I am not a cognitive psychologist. I'm someone who came across some cognitive psychology research and went, maybe this will help. And so that's what created this introduction of using cognitive psychology and research into introductory statistics to help students learn probability. And I created this idea of this laddering process, and I want to share with you some results that I've experienced. Okay, so my introductory statistics classes have a lot of students. We are dealing with a lot of math baggage coming into the classroom. I'm sure you guys all have experienced the same thing. You folks see this in your introductory statistics courses, where especially those for non-STEM students, we're really seeing a lot of math baggage, whether or not they have dread, anxiety, they don't want to be there, and they've got a lot, they're bringing a lot to the table. So my large enrollment classes, the sizes aren't helping any, right? So we have at least 150, sometimes upwards of 350 students in an auditorium, but they do have the opportunity to go into small recitation sections. These recitation sections are usually held by a GTA who works closely with me. They attend my lectures. They are doing everything that I'm telling them to do in their recitation section. So those are nice and small. They meet twice a week for 50 minutes, where our large enrollment classes meet twice a week for about, let's see, an hour and 15 minutes. So the small recitation sections are very, very helpful for getting that small group experience, and I utilize those doing the probability unit. So first, before we do this, we've got to play a memory game, right? So it's probably been a while since you played the memory game. I'm going to show you a list of 30 words. And then in this list of 30 words here, you're just going to, during the time, don't write anything down, just try and memorize as many as you possibly can. And remember, when the time is up, the words are going to disappear, and you'll be able to either write down as many words that you would like in the chat, or you can just do it on a piece of paper as well. All right. So here are our words, and the time begins now. All right, time is up. Now, if you want to grab a piece of paper, let's check to see how many words you remembered. You're welcome to put that in the chat if the chat is working. It looks like I see somebody who's raised a hand. I'm not sure, Kelsey, if you can see if maybe they can't access the chat after all. In that case, you can write down as many as you can on a piece of paper. Give you a few. Oh, yay. Gibby, you used it. Thank you so much. Oh, thanks, Nan. I appreciate you telling me that. Okay, great. It's been a long time since we played this game, I'm sure, with yourselves or with anyone, but it's to illustrate how it's not easy to remember a lot of things at once. So let's see if you've written some of the words down. I can go back there and you guys could see if you remembered words correctly. Sometimes we make up words that don't exist in the memory game as well, which is kind of interesting that our minds do that. And of course you're like, oh yeah, that's right, that's right. Well, I mean, again, this idea of cognitive load, it's definitely something that has been around for a while. Sweller talked about that in 1988 in his paper, Cognitive Load During Problem Solving. And it's about how much information that our working memory can really hold at one time. And since working memory has a limited capacity, our instructional methods, according to Sweller, should avoid overloading with additional activities that don't directly contribute to learning. So using this idea, we're seeing that, we can only hold so much here in the memory game, right? Well, inside of probability, I realized after looking at this, there is an enormous amount of cognitive load. So let's first look at the blue line here. What's the chance process, the experiment, the trial? In probability, they're games, right? And it's not always the same game. In fact, it very rarely is, right? We have decks of cards, we have roulette, we have die rolling, we have all sorts of things, coins being flipped. I mean, all sorts of different chance processes here. So then, all right, what are those events? What are we interested in? What's the sample space or the outcome set? What are the possible outcomes that we can get? What's all the probabilities that entails? And then, well, what are we trying to solve? What probability rule should I use here? And how do those rules work for that problem situation? Am I using the right rule? Okay. So there's a lot that students have to take in and process and deal with every probability situation, especially students who are non-STEM learners. All right. So again, too many choices, right? Too much going on, overwhelm. So how do we reduce the cognitive load like Sweller suggests? Well, first of all, cognitive science has shown that seeing worked out examples first makes tasks easier and results in greater understanding in less time. All right, well, let's think about it in our own lives, right? Like when we see something happen first, we process that information. We're like, how do we do this, right? Like, well, let's see how this is done. Let's see the whole process. For instance, somebody doesn't just tell you to swim and explain the process of swimming, and then you jump in the pool and see if you can do what they told you from an academic standpoint, right? We got to see people swim. We've got to watch that actually take place. So looking at actual problems being solved ahead of us, but ahead of the students, and delay actual attempts at problem solving benefits learners who are new to this content. And this is something that Atkinson, Kirshner, and Rankel all worked out in this early cognitive psychology. This was not regarding statistics per se. This was just looking at actual problem solving practices. Okay, and so Further, then Brisbane in their article in 2019 actually did do this in a statistics class. It wasn't just me. It's the only other article I could find that introduced these concepts into an introductory statistics class. And they studied worked out problems and they demonstrated better performance on different statistical concepts, not just probability. So the great thing about what we're talking about today could be used probably anywhere in any unit, in anything besides, even in mathematics, chemistry, things like that. So I invite you to see how you would like to take this on and utilize it this semester. So let's first look at worked out problems and additionally adding self-explanation on it, because that's kind of a really important key here. Not just using the worked out problems. And here's the other thing, contrary to popular belief, worked out problems is not doing problems on the board for students. Okay, so let's make that very, very clear. These are fully worked out problems. They have everything from the start to the end in that. And so students are seeing the entirety of the problem worked out in front of them. And then they're going to be using something called self-explanation. They're going to decide why those steps are correct. And if students can actually discuss in small groups how that works out with each other, you could use breakout rooms if you're in Zoom. You can actually enhance learning even better than if they just are trying to self-explain on their own. So self-explanation is really truly about why and how that correct answer is obtained. Like, why are we going from this step to this step? Why did the problem utilize this process? And so it begins to mentally form some really great understanding. And then the best article is Riddle Johnson's in 2006 that they showed that learning even improved without getting instructor feedback to the explanations. So I'm telling you right now, I did not grade the students' responses. I let them work together in their recitations, and during the lecture. It took about a week for this. So that's 2 lecture periods, 2 recitation periods. And I did not grade any of their self-explanations. They're working together, and this article, I mean, let's use it, right? So the next step in this laddering process to reducing cognitive load would be to then introduce partially worked out problems with self-explanation. Now, again, this is all part of this process that took a week. The first recitation period, they used the worked out problems. The partially worked out problems was the second recitation period. And then again, that helps lead them into obtaining the solution, so that what's missing, if they add that, would give them the answer. So this again is like a laddering process. Then the third part is the incorrectly worked out problems and self-explanation. Now, you could use this in a worksheet. You could do this in a large group. I use the incorrectly worked out problems in a large group. And again, all of that is in the appendix in the article. And you're welcome to utilize whatever you want, as long as you understand that this was my first attempt at that. And so things are getting refined, of course. The more we do something, the better it gets as instructors, right? So what I did is I proposed this incorrectly worked out problem from our text. And it was a funny example, and had the students look at that incorrectly worked out problem as well to see what went wrong. I'll talk about that here in just a little bit too. But here's the article in 2013 here, where, you know, they really took this intentional solution errors and said, okay, can students find the mistakes, correct that problem solving trajectory, and solve the problem correctly, definitely improved learning as well. All right, so here's our laddering process for reducing cognitive load. We're providing these worked out examples, fully worked out, not just doing them on the board for them, right? So they're seeing the whole process done. Then take away parts of that process and provide partially worked out examples. Then even provide incorrectly worked out examples and employ self-explanation through this entire process. And then let's have them swim, right? Let's have them actually jump in the pool and finally do some problem solving on their own. So the best thing that we can provide our students here, especially in an introductory statistics course where there is so much information, is to give them a little rest in the brain, right? A little less cognitive load, reducing that cognitive load. Well, here's a couple of examples from the situation that I utilized. Here's the very first worked out problem where I had the students study these worked out problems, and on the right side, so here's you can see here that it's the probability of getting a 6 on the first and a second and a third roll of a die. Okay, so they want to roll all sixes. And this is actually a student's work I took a picture of here. In my undergraduate class. And then you can see that they recognized a keyword. They even circled it in their work. I asked them a couple of questions to help prompt some of this self-explanation, right? Like, why is the fraction 1/6? Okay, well, they're like, well, there's one side on the dice with 6 total sides. Why is the 1/6 multiplied by itself 3 times? Okay, well, you've got 2 girls and a boy. All right, interesting. All right, so I mean, they're talking about it. Now, I attended many recitations just to listen to them talk. And during these recitations, I overheard some students like, okay, I get that I need to multiply, but I don't know why I need to multiply. So this was prompting some conversation that normally would not have happened, which is really interesting. So finally, this pair of students, I had these students work together in pairs for this process of worked problems. And I had already gone through, just FYI, in the class, I had already gone through like an introduction. I used the Monty Hall game, introduced probability. I had done some lecturing. That was our first lecture time. And they'd already seen some examples. And so they knew the basic probability rules when they got to this worksheet, okay? So they called me over and they were like, all right, why is this working? Why do we multiply? Like, why? Like, I know that it's supposed to be multiplied. I know that it should, but I don't know why. So this prompted some conversation. Some students in the rest of the stopped doing their self-explanations and they were starting to listen to our conversation. And I said, all right, let's all go ahead and look at this part of the worked out problems, which this question had them multiply and use the multiplication rule and the addition rule, but I also had them list the outcomes here. And so in this situation, where they wrote all 36 possible outcomes down, and then they were like, okay, looking at the first roll being the same as the second, meaning that they would roll doubles. Another way to talk about this is rolling doubles in a 6-sided die. So looking at this, they were able to see, okay, there's the 6 outcomes out of the total 36. And they started talking about, okay, so if I list all the outcomes, if I add, it doesn't make sense, right? Like I won't get the entire sample space. Okay. So that helped them see that, yeah, multiplication needed to happen. So here's another example of a fully worked out problem as well. I mean, I just led them to this to have them write the outcomes down so that question of why are we multiplying, why is that the case? And they were able to see, oh yeah, okay, I got to get the total number of outcomes, right? So if I'm rolling a die 3 times, I need to times 6 times 6 times 6 to get the total number of outcomes. So here they notice the multiplication and addition rule because they're independent and mutually exclusive. They noticed some key words in the question. They were able to verify that the rule and listing the outcomes worked. And get the answer in this specific example. So there were about, I would say, the worked out problems on the worksheet was 1 page, 2 sides. All right, both sides of fully worked out problems like that they would see here, and that they would then have to self-explain in pairs. Okay, here's another one where they utilize the subtraction rule. And this is, of course, asking, well, what's the chance that at least one rolls a 6? Okay, so looking at how this was written out in words, and again, in our textbook for our introductory class, we do not use a lot of notation. I'm using Friedman, Pisani, and Purv's text and that basis of pedagogy. And that's just the statistics text that was written out of Berkeley. And so we just try very, very little mathematical notation as possible. And so here's that worked out example. So again, in this space, explain why the work on the left is correct. Answer the following questions, again, to prompt conversation, prompt them to say what is going on. And one thing that I really love to see is that they talked about here, this student said, well, the subtraction rule with the keyword being at least one, and then I've got to use the opposite of least one is none of something. Okay, all right, I like to see that, all right, we're processing this, we're learning why this is the case. They're assimilating this into their own knowledge, which often in the articles I pointed out, specifically Rankles in 2002, they point out, hey, you know, one thing that is missing when we lecture and we just do problems is this process of assimilation. So when students actually see worked out problems and they use self-explanation, they're assimilating this into their own knowledge, right? They're actually having to accommodate that learning and not just having it roll over them, right? So why is the fraction 5/6? Why multiply? All right, so it's all three of them rolling the dice. Again, we've got the two girls and the one boy who are rolling the dice, each rolling a die. And then this student didn't, you know, really explain like 5/6 per se, but again, it's okay. We need to let go of having this control over the self-explanation, right? So they're getting at it. The student probably understood, oh yeah, well, if we're not going to get a 6, there's 5 outcomes, but they didn't have to write that down. Again, I didn't grade any of this. I only graded the problems that they had to do after all this was done as a homework assignment. All right, so here's another example of the subtraction rule. This one is not all 6s in 3 rolls. So how do they, you know, what's the chance they do not roll all 6s? Again, this student recognized subtraction because all and not all are 1, which is interesting. I like this wording here. It equals 100% minus the opposite event. Okay. Yeah. And also in this text, they talk about the complement being an opposite event as well. So again, we don't use a lot of that high technical verbiage. So my students are recognizing, oh, the opposite event. So together they add to 1. What are the keywords? They're, you know, okay, not all, processing that. Now I find the subtraction rule is very difficult for them. They miss that the most out of all of the rules: multiplication, subtraction, and addition rule for this basic probability lesson. And that's pretty much all we cover in introductory statistics. We don't get into Bayes' theorem or anything like that. It's just a very gentle introduction to it. But the subtraction rule has always been so hard for them. So one thing that this really did is I wanted to see how that would work for them. And I think the cognitive load here, I mean, I'm not a cognitive psychologist, but I think the cognitive load is just so heavy with the subtraction rule, right? I mean, they've got to solve a completely different question to get the question right. They had to solve getting all 6s in 3 rolls before they can subtract it from 1 and actually answer the question that they're looking at. So there's a lot going on here. There's the multiplication rule inside of the subtraction rule here. Now, this is some examples of partially worked out problems where I had this example, finish the problem. So in this specific example, the problem was posed. You've got, trying to remember here, I'm going to pull it up really quick. They were posed, I apologize, in my PowerPoint slides. All of my notes disappeared. I don't understand why they disappeared, but they did. So fun. Here it is. An elementary school employs 15 teachers, 11 are women and 4 are men. 2 teachers are selected at random to meet the governor and attend a reception. What's the probability that both selected are women? Okay, so that's the question that they're posed here. And then you can see the partially worked out problem. So both selected are men or women in this example. I had part A was both selected are women. And then this part was both selected are men or women. So you need a man and a man or a woman and a woman to go. What's the chance of that this happens? So what's interesting here in this example is that this student right here, there's some eraser marks. And what this student had written down before, you can see is a very common mistake, doing multiplication dependent rule. And they forget that, okay, we have to do the conditional probability first, that the first man was selected. And now what's the probability that the second man was selected given the first one was selected? And so I loved seeing that there was a mistake made. They went back and corrected that and knew right away, again, for the women being there 11 women out of the 15 women, then that would then be 10 women out of 14 for the second selection. And again, here's the self-explanation. Again, I just provided some prompts. They're not fabulous prompts, but they're just prompts to get them talking and to write down some ideas. Okay, so why is the fraction 11/15 and the next fraction 10/14? Okay, the first female teacher has already been chosen without replacement. So they thought of this as like a, in a box model with or without replacement type situation. So loved to see that. All right. So how did that work out for you? Okay, so let's first just make sure now, after this process was done, what did I do? I set them loose. Okay, we went through this process. And again, I said, okay, here's the worksheet. This is now your homework assignment. And they just had some probability questions. Now, the interesting thing is that these were the exact same probability questions I asked in a prior semester. But this time I had spent the first few problems going through worked out examples and partially worked out examples before having them finish it. So I didn't ask any new questions. I didn't have the same, I didn't add to the amount of homework that they had. So again, they just had some partially worked out and some worked out problems. And then the remaining problems, I had them work out on their own. This was the exact same worksheet that they got in a prior semester, where it was just basically like, go to it, have fun with that, and best of luck, right? So then I had the unit test on this. Again, now I ask these, I have large lecture sections, so the unit test is randomly obtained from a test bank. And the test bank here asked the exact same questions both semesters. So I was able to do some comparison as to how these students actually did. So there was a question just on the definition of probability, like what is probability? And this is also available on as the appendix to the article as well. So you can get access to that. But the definition of probability obviously went up, which they understood it as a chance process, which is pretty cool. The definition of mutually exclusive. Now, interestingly, that's quite a jump as well. I have struggled with students understanding mutually exclusive events, and for them to be able to recognize mutually exclusive events, almost all of them getting it right this time around. Again, these are these tests, they're not able to see it. So it's not like they're compromised, just know that. The students take it and they move on. So it's not compromised from semester to semester. I'm still using them now, a couple of years later. Here's the question on the dependent multiplication rule. 83.6 to 85. Again, students generally get this with practice, which I find interesting. But again, I talked to you already about how the subtraction rules just tend to be so hard for my students, and that increased quite a bit. What's interesting overall, in these 81% of students correctly solved the exam questions, which was a 19% increase from the prior semester. So looking at this item by item analysis, this was really improved here. So again, the combination problems, the addition and multiplication rules, when we have the combination of both of them, that was an incredible jump, okay, as well. So I was like, okay, I'm sold. This is a neat way for us to utilize this idea of a laddering process to reduce cognitive load. So again, the cognitive psychology literature is talking about using worked examples, partially worked examples, some incorrectly worked examples with the employing self-explanation, and then let them go. Then let them try some problem solving practice. Now, as I said before, this was done over the week. Okay, so I did give them some basic probability understanding via lecture before I had them do the worked out examples on their own. So they were familiar with some of these items. And of course, here is a lot of references. Again, you can find that in the paper. And thanks again for coming to this awesome learning workshop today. And I'll turn the time back over to you.
Thank you, Kimberleigh, Professor Hadfield. We are getting close to the end and being just about out of time, but I wanted to open it up for questions. So if you do have any questions, please feel free to enter those into the Q&A box or the chat. We'll leave that open for another minute or so.
And there is a question right here. Let me
Yes.
see if I can answer. Is that okay if I answer this?
I was just about to read it out loud, so go ahead.
Oh, awesome. So the question is, if I spent the same amount of class time on probability, or did this method take additional class time? And no, it did not take any additional class time. This was done over the same amount. So what was interesting is that because the students were asked to work in pairs and work together, that was what was normally used in terms of class time for them to just, plow through that homework worksheet, right? And just hit these problems head on. So sure, I'm happy to put the paper in the chat. No problem. I can grab that right now and throw that in there. So that's the DOI. To actually access the appendices and, just the worksheet, like I said, yeah, don't think it's expert, right? That was the first time I used it. So of course it can be fixed, and I'm sure you guys would create better work there, but that's available on the website of the teaching statistics actual journal. Okay. And do I use this method for all topics? No, but it absolutely could. And that one article that I referenced here, right here, it was the one from 2019, Brisbane and Nascimento. They used the methods in several of their topics throughout the semester. So they did that and compared it to a control group where they didn't. So it was a very interesting study. They did it for several different topics. So I don't personally do it for all topics. I don't have that kind of, unfortunately, time, but it's something that I now tell my students, look, if you, I provide them and say, you do them on your own. If you self-explain, if you do this, then you have that. It's been proven in the research that it does increase your learning. So great question, Art. Thank you. It's a journal article. The article itself is available to everyone. And if you just go to that online library at wiley.com, and then I put that in the chat, you can access the teaching statistics journal. Okay, you don't see it? Okay, yeah, I'll be happy to put that back in there. Let's see, it should be, oh, maybe it's, I don't think I put it in right. There we go. Thank you, William. I'm so glad you said that because I didn't put it in the right one. All right, thank you. You bet. I'm so glad you said that. I guess there's a question too. Is this going to be available for everyone? Is it recorded? It looks like is the question.
Yes.
Okay.
The presentation has been recorded and we will be posting it on our blog. So all of our webinars are recorded and posted so everybody can go and reference them and access them later on. And kind of on that note, if you or any of your fellow instructors are interested in presenting for this Learning and Growing webinar series, I'll be chatting in a link as well for you to submit proposals, because it looks like there aren't any further questions. So I've just linked that in the chat. Wanted to give you all a moment to check that out. And if you have any further questions, you can always direct them to us at marketing@hawkslearning.com. And we'll be also emailing a link to view the recording of this webinar once it's available. But again, I wanted to say thank you to Professor Hadfield for your insight, knowledge, and taking the time to share everything that you did with us today. Thank you to those that have attended. I hope everybody has a great rest of the day, and y'all will be able to access that recording shortly.
Have a great fall semester, everyone.